All right, hey everybody, this is your lecture that you're going to watch while I am out of town at a conference. Remember, this is built into the syllabus, all right, that you don't have class this week. All right, so Oceans and Seas, but before we get there, we're going to talk about our scientist of the week. Her name is Dr. Maggie Ibunalua Aderin Pocock. She was born in the United Kingdom, and when she was a child, she told her teachers that she wanted to be an astronaut, and they encouraged her to go into something a little less scientific, like nursing. All right, not that nursing is any easier. This was just an unfortunate stereotype. All right. But no one knew that while Maggie struggled really hard with reading and math, it was because she was dyslexic. So it took quite a few years for this to discover, which isn't uncommon for many children with dyslexia. And once they figured it out and provided her the support she needed to succeed in academics, she took off. She has a PhD in mechanical engineering. She has degrees in physics and astronomy. And her science focuses on developing new technologies for telescopes to improve telescope function. She's worked on some of the most famous telescopes in the world, like the Gemini telescope in Chile, for one, which is an incredibly cool telescope. So she also, speaks to children every year. She goes around to many parts of the UK and to other countries, and she tells kids about who can and cannot be a scientist. And she uses herself as an example. So there's preconceived notions about who is and isn't in science. And she says, well, I, am a black woman with dyslexia in science. If I can do it, you can do it. And what this does is it shows kids role models that they can look up to, different people in science succeeding. So because of all this incredible work she's done, she was actually named a member of the Royal British Empire by the Queen. So she got to meet the Queen fairly recently. And I think that's pretty cool. So here is a quote from her. Imagine a dyslexic from London meeting the Queen of England. It's mind-boggling, but that shows how much potential you have. And I think that's just a beautiful way to look at life. Anyway, so there's our scientist of the week. I'll post a little blurb about her later, but she's pretty awesome. All right, so oceans are the largest feature on Earth's surface. They cover 70 to 75% of the Earth, but they're pretty much a realm of mystery for most of human history, and still now. All right, so I'm not going to ask that you memorize any of the human details that we're talking about here, but it's kind of a cool story, and you should know a little bit about it, just, for your general edification. So the HMS Challenger, HMS stands for Her Majesty's ship, was in the late 1800s and was operated by the British Navy, and this was the first investigation of the seafloor. So how they did this was they took a 5-mile long weighted rope. There's a weight at the end, and you drop it slowly into the ocean. And when it hits the ground, you take a measurement. You see how far it went into the ocean. As you can imagine, this is a pretty painstaking process, but this is how we started learning about the ocean. Once we got to the 20th century, we started using the reflection of sound waves and echo sounders. And of course, this took off based on submarine technology during World War II. All right, now today we use sonar beams, and so we can take wide profiles of the ocean floors. And of course, this is much faster and paints a much more accurate picture. All right, and here are some sound waves. So we can shoot sound waves into the ocean and see how long it takes them to bounce back. What you're looking at here on the bottom, these lines, these are uninterrupted layers of sediment. All right, and you can see where there are interruptions, those are actually structures in the ocean floor. So it's kind of like painting a picture of what's there. It's pretty cool. All right, we also can use orbiting satellites. We can see surface variations of 3 to 6 centimeters. This is incredibly specific all the way from space. So, anybody remember who made the first map of the ocean floor? So, Marie Tharp made the first map of the ocean floor in the 1950s. And this corroborated the theory of plate tectonics. All right, so plate tectonic theory. She understood that there was seafloor spreading, meaning divergent plate boundaries, right? So that was Marie Tharp. Her ideas were originally dismissed as girl talk. However, she proves to be one of the greatest scientists of the 20th century. All right, so along the ocean floor, we have broad volcanic peaks, deep trenches, extensive plains of flat ocean floor, mountain ranges, and large plateaus, elevated pieces of land. All right, so the ocean floor is not very simple. It's very complex. but we've only mapped about 5% of it. Why only 5%? If we have all this cool technology, why only 5%? So one of the places that we have mapped extensively is Hawaii. Well, one of the reasons we've mapped Hawaii is because there's a lot of geologic interest there. All right, we only have about 100 ships in the entire world with the capabilities to do this sonar. And we would need about 100 years to map all of the ocean. So this has a bunch of limits, financial limits, right? Scientists can't do this stuff unless they get money to do it. And there's not a lot of places that want to give money to sonar a place in the ocean floor where it doesn't look like a whole lot's going on. 2, the time to do it, 100 years. The number of scientists required to do it. So it's really difficult to get all these variables lined up. So we're going to break down what the ocean floor looks like. There's 3 major provinces. We've got continental margins, deep ocean basins, and oceanic ridges. Oceanic ridges are mid-oceanic ridges, and if you take a look down here at the very bottom, you see a cross section. If you see any slides of the red star in the corner, please don't pay attention to them. I forgot to remove some of them. They mean nothing. All right? So if we go from A to B here, right, this cross section across this ocean, obviously this is the Atlantic, stretching from North America to Africa, we see the continental margins, where we're closest to the continents, all right? The deep ocean basin, where it's relatively flat and quiet, and near the mid-ocean ridge. Well, you'll notice there's a lot of ridges. All right, so let's start at this continental margin. All right, this is the zone that separates thick continental crust from thin oceanic crust. Now, take a look at the 2 basic types of continental margins here. On the right, we'll start with the one on the right first, we have what's called a passive margin. Passive means lack of activity, all right? So what this means is there's no active plate tectonic activity near that area, all right? And you agree with me, because how many earthquakes and volcanoes are there on the eastern coast of the U.S.? Very few. That's in opposition to the west coast, which is what's called an active margin, where we have a lot of subduction and a lot of volcanism, right? Anybody remember what that's called? I assume you're yelling the Ring of Fire. Awesome, good job. All right, so there's 2 types, passive and active. All right, so passive margins, again, like the eastern coast of the U.S., all right, and the eastern coast of South America is also a passive margin. All right, the western coast of Africa is primarily a passive margin. All right, pretty much all of it. All right, so passive margins are found along most coasts in the Atlantic Ocean. All right, so here's an example of some of our passive margins. They're pretty far away from plate boundaries. So let's take a look at South America, because we can see this one really easily. Take a look at the right side of it, the east side of South America. You see where they're pretty far away from any activity. But on the west side, you see the Nazca plate right there and the Cocos plate. And you already know a little bit about the Nazca and Cocos. We've talked about them. They're actively subducting and causing major earthquakes and volcanoes. All right, so along passive margins, there's 3 primary features: the continental shelf, the continental slope, and the continental rise. The continental slope is a gently sloping submerged surface extending from the shoreline. So you can see that there, it's a gentle slope, fairly shallow water, all right? And it's still composed of fairly thick continental crust. And what this is it's actually the continent that's flooded, all right? So parts of the U.S. are flooded. If we dried up all of our water into ice, right, and if we lowered those sea levels, we'd see a lot more continent. All right. Well, right now, though, however, we're drowning more and more and more of the continent. We can see that happening. All right. And that's because of global warming, melting of the ice. All right. So the continental shelf is usually about 50 miles wide. Okay. So what you're looking at here is the UK, and the UK is actually not separated from Europe by an actual ocean. It's just a flooded extension of the sea. All right. So there's actually land underneath there. All right. So I don't need you to know this, but the continental slope of the average slope of the continental shelf, is about only 0.1 degrees. So it's very flat, but it does have a slight gentle curve to it. Okay? And I don't need you to know how much it is, just so there you know. All right. So here we have the continental slope. You can see that that's going to be one heck of a dip as compared to the continental shelf. All right, there's going to be a sharp change, and that's due to the boundary between continental material and oceanic material. And of course, oceanic material is much more dense. All right, this can be very steep. you can in many places scuba over the continental slope, continental margin divide, and it's pretty terrifying looking, though you just can't see anymore, right? It gets very dark. All right, so you can see that in a lot of like shark movies. All right, it's usually only 12 miles wide, so it's much thinner than the previous piece of information we talked about. All right, that continental shelf. And then finally, the continental rise. This is where we have a thick accumulation of sediments. This is where a lot of our deltaic material, remember all that stuff coming out of rivers and then into deltas, all that fine-grained material, a lot of it falls during the continental rise. All right, so that's where we have so much sediment building up. All right, and a lot of it's also moving down by something called turbidity currents. Okay, so turbid means a violent movement of something. Okay. So how turbidity currents work is during most major storm systems, you'll get lots of heavy waves, and this will promote a lot of these turbidity currents. All right, so let's play this video here. Turbidity currents are essentially underwater landslides, almost like an alluvial fan, like a landfall on land. All right, so it's an underwater landslide. They transport a ton of sediment, and they create submarine deep sea fans, which look just like alluvial fans. Okay, so they spread out in a nice triangular shape, except they're happening underwater. All right, so this is kind of what they look like. They happen a lot after major storm systems. Pretty neat, right? So here's it coming down. As you can imagine, the largest pieces of material fall first. The lightest pieces of material fall last due to gravity. All right, make sure to watch the rest of that video on your own. It's pretty cool to look at, but you can see the biggest pieces falling first right in that example. All right, the mud-sized grains will of course fall when that water level reaches 0, so it will take a while to settle. All right, so these can flow for a pretty great distance. All right, and they're going to show something called graded bedding, which means we have the biggest pieces on the bottom, smallest pieces on the top. All right, so active margins. These are the plate boundaries at the margins. Excuse me. All right, and these can happen at convergent or transparent boundaries. And we can find a lot of these in the Ring of Fire. So as an example, the U.S. West Coast. All right, so here's an example. Same map that we've looked at, West Coast of North, Central, and South America. All right, so unlike the gentle continental rise and the slope, we're not going to see that here. What we're going to see is a abrupt deep sea trench, deep ocean trench, and that's being caused by the subduction zone that all convergent boundaries have, or not all convergent boundaries, all oceanic convergent boundaries have, excuse me. All right, this trench can be pretty close to offshore, about 30 miles is one of the closest, so one of the examples of the closest one here is on the western side of South America. All right, so sediments wash down from these continents and they get stuck into this deep ocean ridge. As you can imagine, a lot of sand and dirt gets into this. When the oceanic plate is scraping against the continental plate, you get something called an accretionary wedge or an accretionary prism, which is something we've talked about, and you can see it marked on that map on the left there. All right, do you remember this? So, an accretionary prism is at high or low temperature. If you're thinking, well, it's not buried very deeply, then you would be thinking low temperature, and you'd be correct. Now, what about pressure? This is pretty high pressure. All right, do you guys remember the name of the rock found here? It's a metamorphic rock called blue schist, usually. It's pretty rare to find. All right, so some subduction zones have very little sediment, all right, but many have lots of sediment, okay? And it depends on every type of plate boundary. I'm not too terribly worried that you understand this. Just know that it's not the same across every single plate boundary. Everyone's different. All right, so we moved off the continental margins. Let's go to the deep sea basins, deep ocean basins. All right, these basins are about 30% of Earth's surface, so that's about the same as dry continental land. Fun fact, we know more about the moon and Mars than we do about our deep ocean basins. So here are some excellent examples of some of the weird stuff down there. Take a look at the bottom left. That's the anglerfish. That is a female anglerfish. A male anglerfish is teeny tiny, and it is a parasite that attaches itself onto the female for the rest of its life. All right, many of these are translucent, and they have special bioluminescence in them that allows them to be this color. Pretty cool, right? All right, so what we have down there are things like deep sea ocean trenches, or deep ocean trenches, abyssal plains, which are really flat, We have seamounts and guyats. These are the volcanic peaks. And we have large flood basalts of oceanic plateaus. Remember, basalt is a mafic igneous rock. All right, so deep ocean trenches. They're giant, long but very narrow. These trenches are, of course, subduction, so happening in convergent plate boundaries. Most are in the Pacific Ocean, in the Ring of Fire. All right, they are huge geologic features. So this is where we have active subduction taking place, where that oceanic plate, and again, which one is being subducted? The oldest oceanic plate. It's the most dense because it has cooled the longest. All right, so that one is the one being subducted. So these trenches can exceed 3 to 4 kilometers, but that's the average below the surrounding ocean floor. They're the deepest surface features on Earth. So 5 trenches in the Pacific exceed 33,000 feet in depth. These are ridiculously deep, okay? So the largest or the deepest trench in the world is the Mariana Trench. The trench itself is deeper than anything is tall on Earth, so it's deeper than the Himalayas are tall, for example. It's 36,000 feet. All right, we have managed to get to the bottom of the Mariana Trench once. All right, so the Challenger in the Deep Mariana Trench, okay? So we made it there a while ago, and this trench is deeper than Mount Everest is tall, okay? Sorry, not the Himalayas, I meant Mount Everest, all right? But they were both created by convergent plate boundaries, which I think is kind of a cool point to make, right? Both these really, really tall mountains and these incredibly deep trenches were made by convergent plate boundaries. Just depends on the type of crust making it. All right, so again, humans have reached the bottom of this trench once. In an unmanned submersible, reached it once. In contrast, humans have stood on the moon 6 separate times. All right, and again, I don't need you to know any of this information about the Navy and stuff like that. That's not what this class is focused on. But if you find this kind of stuff cool, I've included this information for you. All right, now let's move to the abyssal plains. These are the deep, incredibly flat bottoms of the ocean, and they cover 40% of deep ocean basins. They're found everywhere, but the Atlantic Ocean has the most extensive abyssal plains. Why does it have the most extensive abyssal plains? Because it's divergent and it's seafloor spreading. All right, so they occur at pretty great depths. All right, so they're the deepest parts of the ocean that are not actively in a trench, and they're the most unexplored region on Earth. We know almost nothing about the abyssal plains. All right, they're incredibly flat. They have less than 3 meters change in elevation over 800 miles. So what I'm saying is there is a place on Earth that has less topography than Florida. I know what you're thinking. Impossible, but it's not. All right, so the reason it's so flat isn't because there's nothing there. There's actually a whole lot of seamounts and stuff down there, so like little baby mountains. But we have so much sediment covering the bottom of the ocean. So it overlies all of the oceanic crust. There's over 3 miles of sediment. And where is all that sediment coming from? Well, it's coming from places like deserts. Deserts blow fine, fine sand all over the world. It's coming from mud coming from the coasts. And it's coming from things like fish poop. All right, there's a lot of fish in the ocean, and they all poop. And that poop actually traps other little pieces of stuff and pulls it down and falls to the bottom of the ocean. So a lot of that stuff on the bottom of the ocean floor is just straight up poop. All right. A lot of it's also from turbidity currents. All right. So the rate is about 2 to 3 centimeters per 1,000 years. We can tell how long it takes because we can put a drill down there and pull up some of those cores, and we can date those cores using a number of different methods, namely radiometric dating. All right. Lots of volcanoes. Okay. The most of them are in the Pacific Ocean. And hopefully you're thinking that makes sense because the Pacific Ocean is, of course, an active subduction zone. All right. They can be very, very tall, but they're quite numerous in number. There's more than 1 million volcanoes in the oceans, and there's way more in the ocean than there are on land. So just remember that. They tend to form in long chains. All right. Each volcano being created as a tectonic plate moves over a hotspot, kind of like the Hawaiian chain here. So this is the Hawaiian island chain. All right. There's a big arrow pointing to the larger island. All right. So if the volcano grows fast enough before plates move away, it can reach the ocean surface and an island can be formed. There are tens of thousands of these islands in the Pacific. There's a few in the Atlantic, but most of the time they're in the Pacific. So this is exactly how Hawaii was formed. All right, and hopefully you remember that. Hint. All right, so here is one of the few examples of the Atlantic Ocean volcanic islands. This is Tristan da Cunha in the South Atlantic, and it is the most remote human settlement on Earth. All right, this is a volcanic peak. This was created by one of these seamounts. All right, so it takes days upon days to get there by pretty much any method of travel. Pretty much the only people that live there, they're tourists that decided to stay. There's not a whole lot of native human settlement there. All right, so there it is. Easiest way to get there is by one heck of a long cruise from Cape Town or Rio de Janeiro, depending on which direction you're coming from. All right, the mid-ocean ridges. These are divergent plate boundaries. Hopefully you remember that. All right, so they're spreading apart. We see tensional stress there. Okay, the mid-ocean ridge system is the longest topographic feature on Earth. It is 43,000 miles in length, and it stretches all across that band of longitude. Longitude. All right, these are 20% of Earth's total surface. They're found in all major oceans. All right, even though they're called mid-ocean ridges, they don't necessarily occur directly in the middle of things. So please remember that. Okay, some spread faster than others. All right, so the term ridge is misleading. They're not long, narrow, steep ridges, but they're actually broad mountain ranges. Remember that they're coming up and they're making mountains. We learned about that then during our crustal deformation day. I don't need you to know the sizes or the widths of these. All right, so these can be about 2 to 3 kilometers, so about 1 and change miles high, which is a major mountain range on land. So here is the island of Iceland. It rises 4 kilometers above the North Atlantic, and it was actually created by mountains from the mid-ocean ridge. Parts of Iceland are actually on that divergent plate boundary still, as you can see. So if you ever go to Iceland, you can actually scuba dive between 2 plates, which I think is about the coolest thing you could ever do on a vacation. All right, so Dr. Harry Hess in Princeton University developed the concept of seafloor spreading based off of data points made by many scientists like Marie Tharp. All right, so 60% of all magma that erupts as lava onto the surface of Earth occurs along mid-ocean ridges. So all of those volcanic movies you see with all the lava spewing out, those are really the minority of lava coming out. They're mostly coming from these mid-ocean ridges. All right, and again, we see all mafic material. It's coming straight out of the mantle, so we know it's heavy in iron and magnesium. And the type of rock that comes out of there is basalt. Now, the shape of the topography of these oceanic ridges are controlled by spreading rates. Okay? So if it's spreading fast or if it's spreading slowly will determine what the spreading ridge looks like. All right? The factor that controls spreading rate is the amount of magma being generated. So the more magma, the faster it will spread. The less magma, the slower it will spread. Okay? Excuse me. So slower spreading ridges, 1 to 5 centimeters per year, such as the Mid-Atlantic Ridge. Okay? What we see here, excuse me, okay, the topography is very rugged. All right, so if it's slowing very, very, very slowly, we see a very rugged topology, and we see a well-developed rift valley between them. All right, so that's what it looks like, that top picture right there. So if it's spreading more slowly, you see those features more defined. Okay, very prominent rift. At faster, those rift valleys are absent. So the magma's coming out super fast. All right, it's far more elevated, but those details are kind of lost. It's much less rugged. Okay, so we can tell just by looking at a picture how fast something is spreading. All right, so magma chambers that are larger and very well developed generally spread much faster. Okay, so we have a lot of magma coming out of it. All right, it's coming out, it's making these giant ridges. We'll talk more about that in just a second. All right, so here's what it can look like. This is false color just so you can see the height of everything. All right, magma is erupting along the pink. You see that the pink isn't always right along that spreading ridge. We can have volcanoes in other areas. All right, there's seamounts on either side of that ridge. Okay, so ocean ridges are elevated for 2 reasons. First, we have the upwelling of magma, which creates that major bulge along the ridge, right? We have that magma coming out. That makes sense, right? Obviously, that's going to make some kind of a ridge. The second deals with the density. Which is more dense, hot or cold rock? This is where you yell out, cold rock is more dense. All right, so hot rock is less dense. And when that magma first comes out, it's quite hot, so it doesn't sink as much. All right, so hot, newly created oceanic rock, which is basalt, has more volume and less density, so it doesn't sink, so it creates a much larger ridge. Okay? All right, so as the seafloor spreads away, it cools by the seawater, and that seawater enters through the rock, through faults and fractures, okay? And it takes about 15 million years to completely cool a rock. It can take much longer depending on the geology of the surrounding area or depending on the rock itself. It can take up to 80 million years, but 15 million years is pretty solidly average. All right, but as it cools, it gets more dense and it sinks into the crust, which is why at that mid-ocean ridge, you see that it slowly gets less steep the further away you get from the ridge. All right, so there's more words on this slide just since I'm not here to explain it to you. All right, but as that rock, again, it cools, it contracts in size and it increases in density, just like we've learned about so many other so many other types of material throughout this class. Okay? All right. So we can see ophiolites on land. So let me rephrase. Ophiolites are what we call oceanic rock that's been shoved up on land. Okay, so this can happen by plate tectonics. It can happen by uplift. A lot of the most famous ophiolites are found in Oman and other bands in the Middle East, but we do see some in California and Newfoundland too, and Cyprus. All right. So ophiolites are just where we see oceanic rock, or oceanic crust that's been pushed up onto land. So we can take a look at what oceanic crust then looks like. All right. We have deep sea sediments on the top. Under it, we have pillow lavas. We have sheeted dike complexes, which are just intrusions of igneous rock. And finally, gabbro. And you may not remember gabbro, but gabbro is the ultramafic rock that forms very, very deep. It's rare for us to see on Earth. Okay, we have to get to the very bottom of the ocean crust to get to it. All right, and then finally below that is the source of the magma. And remember, if it's ultramafic, it's forming at the highest temperatures. All right, so here's layer 1, layer 2, pillow basalt, sheeted dike complexes, gabbro. All right, very, 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 very coarse grained, meaning it cooled very slowly, very mafic. And finally, we have the upper mantle. This is peridotite. It's almost entirely olivine. That's what's giving it that beautiful green color, and it is ultramafic. All right, so this brings us to the birth and death of oceans. This is called the Wilson cycle. All right, so creation of the Atlantic began when supercontinent Pangaea began to split apart, about 200 to 230 million years ago. Take a look at South America and Africa as they pull apart. That is the wee baby Atlantic. All right, so this is formed by magma coming up from the mantle. Remember, this is causing rift basins. Remember the Snickers bar example we gave? Pull a Snickers bar apart and that caramel will droop between it. Okay, we still see some of those rift basins in Durham, North Carolina. All right, you can go up there and see it. All right, there's long fractures from tensional stress that we can line up across the two continents. Plates begin to pull apart, slabs sink, we have a rift valley between the two, all right, and this slowly spreads for hundreds of millions of years. All right, so then we have rifting pushing North America west, Europe and North Africa being pushed east, and the Atlantic mid-ocean ridge was formed. And this has been going on for quite a few 100 million years, 200 to 230 million years. All right, I don't expect that you memorize every step in this, but you should be able to tell me the general process of how the Atlantic was formed by the spreading apart of continents. Okay, we can actually see this happening in the Red Sea. All right, so you see here we have tensional stress and a divergent plate boundary on the Arabian Peninsula and the rest of Africa. All right, spreading has been going on for at least 5 million years, and we know that based on paleomagnetic dating. So we may have a future ocean starting here, and that's why we have so many lakes here. Like right in this little area here, we have Lake Tanganyika, we have Lake Malawi, Lake Victoria. All of these are formed by these rift basins being pulled apart. All right. It will likely lead to a future ocean, although it could fail. That happens sometimes. But we do have the East African Rift, lots of volcanoes there, and that is how our continents are splitting up. Some actually fail. So, for example, there is a rift in Kansas to Lake Superior, highlighted on that map, and it actually just never developed. Happens all the time. Now that leads us to the death of the ocean basin. So, plate tectonics creates new oceans and mid-ocean ridges, and we have lots of subduction. Oldest oceans on Earth are about 180 million years old because of this subduction. All right, so mantle plumes. We know this. We've talked about this a whole bunch. All right, so we're going to not spend a whole bunch of time here, but mantle plumes are hotter than normal mantle rock. They rise at a point not on a plate boundary, large mushroom shape, and that heat allows that magma to rise because it is less dense, and this forces continental rifting apart. All right? So this causes because of decompression melting a lot of the time. So if we have a thinning of the continental crust, remember that decompression melting, if we thin the crust, we lower the pressure, and that allows the heat to rise at a much higher rate. All right? And that's how it erupts onto the surface. And this is actually how Pangaea broke apart in the first place, by these hot spots. We'll talk more about this on Desert Day too. All right? So this large landmass like Pangaea essentially acts like a blanket on top of Earth, and Earth is trying to get rid of some of that heat, so we have that decompression and hot spot formation happening. So that is one of the reasons that why Pangaea broke up the way that it did. All right, so here is an example of a hot spot where South America and Africa were once connected. You don't need to remember Piranha and Etendeka. Those are not words I need you to know, okay? But those are the rift zones that we talk about in geology. All right, well, apparently that was the end of the lecture. I will post some review questions because apparently it got cut off. All right, I will post those online. Anyways, hope you enjoyed this. Have a great week.